So let's first discuss the what working stress method is. Actually, working stress method is one of the design philosophies. Different design philosophies are proposed for the design of reinforced concrete structures. Working stress method is one of them. It's one of the earliest attempts of the design philosophies for the design of reinforced concrete structures. So now we get here the two concepts. We have design. Another is analysis. These are two different terms, each have its own meaning. So first let's see what the design is, what the analysis is. For example, what I can say the analysis, I have a simply supported beam. I have a simply supported beam like this, and it is subjected to some known load UDL W, Newton per meter, kilonewton per meter. So in analysis part, what we do, we analyze this beam structure and find all the force resultants. For example, force resultants are the reactions of the supports. We find in analysis, basic structural analysis, we find R1, R2, R1, R2. We also find if it is an indeterminate structure, for example, it would have been a fixed beam, then there would have come the moments on the fixed ends also. And these are the force, and inside it we see the stress resultants as well, because due to this UDL there will be the compression on the top like this, compression on the top and tension on the bottom. This due to this there gets stresses induced in our beam. Due to those also calculation of those stresses, tensile stresses, compressive stresses also come under the analysis part. And one more thing, there, if this load is not along the axis of the beam, if it is placed on some eccentricity, this beam will be subject to twisting moment as well. Calculation of those twisting moments and all those force resultants are also come under the analysis part. Now the design part of this is, for example, now we know these things. What will be the moment coming on this beam? For example, from analysis part, we took the inputs as our simply supported beam is subject to a bending moment, and it is bending moment maximum comes at the mid span. We Mid span bending moment comes at this point. We took those inputs, and from those inputs, we do the design of our same beam. For example, we have to know the what cross-sectional dimension we will give so that this beam will resist that maximum bending moment. What grade of concrete we will give so that it is safe under this maximum bending moment or safe under this loading, and what amount of steel, reinforcement steel will I give so that it is safe. So analysis part is finding the forces, bending moments acting on a beam due to giving loading. And design part is we are given the maximum forces, maximum bending moments acting on our structure. We have to design the cross-sectional dimensions. We have to choose the appropriate grade of concrete and grade of steel. We have to choose the appropriate cover for our structural member. So this is the basic difference between design and analysis. Then we have another concept here is fundamental assumptions in design. Analysis first. I will briefly give a idea about the what are the assumptions, because you may have already gone through this. For example, this is our simply supported beam, as already I discussed it before. This is our simply supported beam. It is subject to some loading. For example, it bends like this. This is the elastic deflection. It like bends like this. If we take one part of this and we see the deflected shape, we see the deflected shape like this. It gets deflected like this. We will say, for example, if we have taken the beam initially and we will cut the cross section of the beam and say we will see the planes perpendicular to the axis of beam. These would have been the planes like this. And if the beam bends, and we say that this assumption makes sure that these planes which were initially perpendicular to the axis of beam, they still remain perpendicular to the axis of beam like this. For example, this beam axis comes like at this point. If I draw a tangent to this elastic curve and tangent to the plane as well, they will make an angle of 90 degree. So the planes before the deformation and planes after the deformation are perpendicular to the axis of beam. Second, this was the first assumption. Second assumption is second assumption is the variation of the, for example, this was our beam section. The variation of the stresses along the depth of the beam are considered to be linear, like this. There is a linear variation of the linear variation of the strains along the depth of the beam. If it would have been a downward loading, we know that on the top, above the neutral axis, beam is subject to compression, and below the neutral it is subject to tension. So there will be a compressive strains on the top of the beam like this, and there will be tensile strains on the bottom of the beam. These are the basic assumptions which are assumed in the analysis. Now we see this. There is one more concept: linear elastic material. The design and analysis that we The design analysis that we are studying right now, it's only based on the linear elastic material assumption. Later on, when we go to the go further in this course, we will also see the when the beam deforms plastically. We also see the how the type of analysis, how analysis changed at that point. But for the first part of this course, the beam is considered to be linear elastic. Now the question is, what is linear elastic? Linear elastic is, we say that a homogeneous material is said to be a linear elastic if it follows this Hooke's law. Hooke's law is stress is directly proportional to strain. From that we get this, the Young's modulus is equal to stress by strain. This is the linear elastic material. And in all the analysis that we will be performing and design for the elastic material, we will be following this definition. Stress by strain is equal to Young's modulus. From there is another one formula, main important formula that we will be using in the analysis from pure bending. Pure bending. We all are familiar with this pure bending equation is F by Y M by I, where F is the stress, Y is the distance from the neutral axis to the fiber at which we are Finding the stress, M is the applied moment, I is the moment of inertia of that section. No, now this stress in our beam, we see that the stresses are either maximum at the top point or at the bottom point. These are the compressive stresses. Here is the tensile stresses. Why these are maximum? Because if we see it from the neutral axis location, Y is maximum either for top point and either for bottom point. So our maximum stresses will be always acting on the outermost fibers, either tensile or compressive. So moment that will cause the maximum stresses is F max I by Y max. I denoted this distance as Y max. This is also Y max. We can say that this is Y max compressive, Y max tensile. This formula will be also used in the analysis. And I, we all know, is the second moment of area about the neutral axis. One important concept more in working stress method is modular ratio. Modular ratio. Modular ratio is it's actually the ratio of sorry for the disturbance. So modular ratio. Modular ratio is the ratio of elastic modulus of steel to that of concrete. E of steel to E of concrete. So there will be a question why we define this modulus ratio. For example, if we see our concrete section or any section, maybe it's column section or beam section, we see that there is concrete present and the reinforcing steel as well present. If we start doing the analysis, because in a linear elastic model of concrete, we assumed that it should be linear homogeneous. Material should be homogeneous. But if we see our concrete and steel both are present, it's a composite section. So we can't use the definition of stress by strain is equal to elastic modulus. So for that, it's a composite section. So for that, we define this ratio modular ratio, which makes it's a homogeneous section. What we mean by homogeneous section? That this steel area is replaced by equivalent concrete area of equivalent strength. The strength that this steel provides here to the whole section, same is replaced by the concrete area. For that, we define the modular ratio. For this modular ratio is given by equation by code. It is 280 divided by 3 sigma CBC. And it's in clause B13D, where sigma CBC, it is permissible compressive stress on concrete in bending. bending. This modular ratio, it is given in the code. It has different values for the different grades of concrete. For example, if I take M15 concrete, for my code defines sigma CBC for M15 as 5, and corresponding modular ratio M as 18.67. Similarly, M27, we have permissible stress of concrete in bending for M20 concrete as 13.33. Similarly, M25, we have 8.5 and modular is 10.98, and like this. Like this, okay. We can see here a model for smaller grades of concrete. Modular ratio is higher because modular ratio is inversely proportional to the permissible stress of concrete bending, and or we can say that it is inversely proportional to the grade of concrete. Lower the grade, higher the modular ratio, like that. These were the another thing is the cracking moment. For example, we have a beam. It is subjected to some loading. This loading induces stresses to the beam section. When we increase the loading such that the stresses go beyond the permissible limits. For example, for tensor compressive stresses in the concrete go beyond the permissible limits on the top side, due to which cracks will occur. But for that moment at which the first crack will occur, that is called as cracking moment. And for that MCR, the cracking moment, it is given as FCR IT by YT. Now here IT is transformed second moment of area. I already said that we transform the section from the composite section to the homogeneous section, in which we replace the area of steel by the equivalent concrete area. Same IT is the moment of second moment of area when we transform it, and YT is the depth to the extreme fiber. FCR is the modulus of rupture. Now we will go to these will be the basic equations that we will be using in our problem. Hmm. This is our exemplar problem that we will be solving in today's class. We are giving a rectangular cross section of a beam which is having a total depth of 600 mm and a width of 300 mm. It is having four bars in the tension side as tensile reinforcement of diameter 25. These are four rebars of 25 mm diameter. All the dimensions that I have shown here are in mm, and grade of the steel is Fe415, and I assume the grade of the concrete is M20. We have to calculate for this section the cracking moment. First part, let's calculate the cracking moment. Cracking moment. For that, I already first we write the things that we require. First is the modular ratio. Modular ratio for M20 grade concrete. I already wrote it right now. For M20 grade concrete, 13.33. Modular ratio is 13.33. Modulus of rupture, FCR. For modulus of the rupture code gives a equation. It is equal to 0.7 times under root FCK. And FCK is given as 20. 0.7 under root of 20. When we calculate this comes out to be 3.13. You have to take care of this here. FCK is in megapascal. It's if we see that this is in megapascal, this is also in megapascal, but it is the rule. Dimensionally, this equation we will say if we say dimensionally it is not correct, but this zero point 0.7 is also having a this unit. If we change the unit of FCK to some another, this zero point 0.7 will change. So we will have here megapascal units. Here we have under root of megapascal units. So it has also some units. It's not just a number here. So we have to take care if it is in megapascal, we have to put the value as megapascal 20, 3.13 megapascal. First, we will calculate the approximate cracking moment. What I mean by approximate cracking moment? Approximate cracking moment is that I assume this whole section, I will take the gross moment of inertia of this section, not the transformer section. That like this, I transformed this composite section to the homogeneous section by replacing this. This is the area of steel. In this section, you can see that this steel area is completely gone, and this whole section is now homogeneous, fully homogeneous. Here we have already only concrete present. Here the area of the steel has been replaced by equivalent area of the concrete as MST, and we have to take back this area of the steel. That is why we put inside M times AST, and we take out as AST area. This is the equation. We put inside MAST and we took out the AST. That is why we total addition we did is M minus 1 times AST. It is the homogeneous equivalent section. This will be the stresses acting on the beam section, compressive stresses on the top, and tensile stresses at the bottom. Approximate cracking moment is if I will not use the transformed second moment of inertia, I use the gross cross section. For that, first I have to calculate the section modulus. I know for the this rectangular cross section modulus is given by BD gross depth का whole square divided by 6. Section modulus we know na. Section modulus is actually Z is equal to second moment of inertia divided by Y max, maximum distance from the neutral axis. And for rectangular cross section we have BD cube by 12 divided by D by 2. So it goes BD square by 6. From this section modulus comes. It comes out to be 300 is our width, gross depth is our 600 square divided by 6. It comes out to be 18 into 10 power 6 cube. So from this we can calculate the approximate this cracking moment, MCR. MCR. I already wrote the formula for MCR as I by YT. MCR I by Y I by Y FCR into I by YT. FCR I by Y. This is section modulus here, and FCR we already calculated as 3.13 megapascal. That is Newton per square. And we calculated the section modulus already as 18 into 10 power 6 cube. This square goes here, this cube goes. This we come out with 56.3 10 power 6 Newton This if we change it to kilonewton, we will write it like this: 56.3 into 10 power 3 Newton, like this, 10 power 3 For millimeter, we write 10 power minus 3, 10 power minus 3 meter. We get this 10 power 3, we can change it to kilo, and this will go 56.3 kilo Newton meter, MCR. Unit conversion is 1 in 10 power 6 directly. Whenever in upcoming problems, we will see a factor of 10 or 10 power, 10 power 6 Newton mm. We can directly write it to 1 kilo Newton meter. Is the factor conversion. Now we will see the transformer section properties, and from transfer, for time being we calculated the approximate. For time being we calculate the approximate, but now we will transform this section to the homogeneous section and calculate the actual cracking moment. What will be the exact cracking moment? For transformer section we have mm, transformer section properties. Transformer section properties. First we have area of steel. First point, steel area, that is we have for our steel we were having 4 bars of 25 diameter. That is 4 uh, 5 by 4 d square 25 square. Okay, this comes out to be 1963 square. So what I already said, that for transformed area, from gross area we take out the steel area, we take out the steel area and add the equivalent concrete area. That is gross area plus m minus 1 times AST. Let me make the figure here also. What is this? This this is the B for this. This is the D for this. For gross area, if we say AG will be B times D plus m minus 1 AST. Plugging all the values that we already find. B times D uh, 80. B was our 300 and D was our 600 plus M was our 13.33. 33 minus 1. Area of steel we already found 1963. This is this one. Okay. When we calculate this, 80 comes out to be 300 into 600 plus 12.33 into 1963. This comes out to be 2042.03.8 square. Yeah. So first our gross area was BD. AG, if we have seen AG was gross area was different. Now our transformed area has changed to some other thing. From this transformed area, we have to work out all the things now. That is the equivalent effective depth will be the same for the steel, but the depth of the neutral axis and the compression depth of the top compressive fiber and depth of the bottom tensile fiber, those will be now changed because we converted it to the homogeneous section now. Now let's work out the first will be our first thing that we need to calculate is depth of neutral axis. Depth of neutral axis. If we if we assume that, for example, our neutral axis is at this point, and we want to know the location of this. This is now this area is 80. This is not a gross area AG. This is transformed area 80. And we say that it neutral axis depth is y bar like this on the top fiber y bar. Okay. Equating these different two different parts, equating the moments of areas about the top side, we will have transformed area 80 times y bar is equal to b d into d by 2 plus that m minus 1 that we added ast into d, because that the area that we added m minus 1 ast, that we add the effective depth, because we replace the steel area by the equivalent concrete area that is at the effective depth distance. When we solve it for the neutral axis y bar, we plug the values of b 300 into 600, d by 2 will be 300 again, plus m minus 1 13.33 minus 1 1963 into effective depth. Effective depth we didn't calculate it now. I think effective depth we assume it cover of, mm, let's say we assume effective depth 550 mm, into 550 80. 8 transformer we calculated. Uh, we got the value of y bar. When we calculate this, we get the value of y bar as 329.6 mm. Now this y bar, if we see here, this y bar is also the distance of topmost compression fiber from the neutral axis. So we can write yc as 329.6 mm and y tensile as bottommost fiber. This one yt yc. Yt will be the gross depth 600 minus 329.6 mm. This comes out to be 270.4 mm. And also the distance of the reinforcing steel ys from the neutral axis. Ys, this is total up to this effective depth is 550. When we subtract this y bar distance from this, we will get this distance. Why? Because we require all these distances. Yc is equal to 550 minus 329.6. We got this as 220.4 mm. Now we got all the distances of the different areas from the neutral axis. For example, we got this compressive area, this compression area, we got it as distance from the neutral axis at yc. We got this area, tensile area, distance of this from the neutral axis. And this transformed steel area yt, it is distance from the neutral axis. So we can now calculate the transformed second moment of area. Transformed moment of area, it. It will be first. Now here is this. We have to calculate the moment of area, second moment of area about this axis. Now this section is at a distance of y. It is having a depth of yc. It will be having a second moment of area as byc whole cube by 3 for this section, this part. And for this lower concrete part, we will be having byt whole cube divided by 3 plus this part. Actually, these both are m minus 1 times ast. This is one part. This is second part. This is third part. We wrote for the first part. We wrote for the second part. Now this is for the third part as mm, m minus 1. This is ast multiplied by y square. This distance, central distance of this equivalent area from the neutral axis. Now this byc divided by 3 comes from this equation. For example, we have now if we have a rectangle of width b and depth d, about the centroidal axis we have bd cubed by 12. This comes to be bd cubed by 12. But for these sections we calculated about the one side. This comes out to be d by 2 again. This is the distance d by 2 also. So we can from parallel axis theorem we can have na about this axis as second moment of area as original moment BD cubed by 12 plus area of the whole section BD times the distance between the axes का whole square d by 2 का whole square. When we work out this comes out to be BD cubed by 3. This is just for if someone is not able to understand from where by cubed by 3 comes. So when we plug all the values of that yc, yt, and ys, we all calculated yc, yt, and ys. We plug all the values. So I transformed will come as we have b values. Let's write b value as 300 and yc we already calculated as 329.64 cube plus we have 270. We are combining these both 1, 2, and 2 terms. 270.4 whole cube as both have same denominator 3 plus 12.3 m minus 1 13.33 minus 1 12.33. I'm writing into AST 1963. The time is 220.4 whole square. This is the distance. Y is distance. IT came out to be 6.733 10 power 9 mm power 4. So now here we will calculate the exact cracking moment. Exact cracking moment MCR. I already told the formula FCR times I transformer divided by YT. It comes out to be, and we have FCR already calculated 3.13 into transformer we already calculated 6.733 into 10 power 9 divided by YT we calculated as 270.4 distance of the bottommost fiber 4. We have MCR as 77.94 into 10 power 6 Newton mm as 77.9 kilo Newton meter. MCR MCR this is exact now. We already first calculated na MCR approximate. If we see MCR, that MCR as that was 56 point something or 56.3 kilonewton meter. This is approximate. This is approx. Which is that when we can consider gross section of the concrete, we underestimated the cracking moment. But the actual cracking moment, when a moment of 77.9 kilonewton meter will occur on our beam section, it will have first crack. Already from the gross section, we will getting 56. That is the lesser from the actual value. That's from the transformed area. That is what benefit we get from the transformation. That is 80, or by calculating IT, we get exact values. From AG, if we start calculating from IG or IG, we get the underestimated values, because here we consider this whole cross section. This was the cracking moment calculation for this problem. From the next week, week 3 will be over with this, I think, uh, limit state methods, and also the analysis at service loads from for working stress methods. In the week 3, we will be taking this analysis problems for working stress and the limit stress method directly. So this was all for today. Thank you.
Thank you, sir.
Thank you. Thank you
Thank you.
everyone for joining.